मार्कर अच्छा नहीं है, देखिए भला इसको नजर आ रही, ठीक है। स्टार्ट करते हैं। अस्सलाम वालेकुम डियर स्टूडेंट्स, welcome back after Eid vacation. I hope you all are fine and enjoying your stay at home. We are resuming our discussion of centripetal force, and before I discuss anything new, anything different, I would like to go over a few things that I have already explained, feeling that after this long gap of many days, a revision is necessary. At least 3 examples can be revised, especially those related to the situations in which centripetal force is related to some angle involved there. Because in simpler situations, force is directed towards the center, there is no angle involved, and we know that force is simply equated to mr omega square or mv square over r. Like in most cases, F is equal to mv square over r. This force, which is always the centripetal force, whatever its nature, it is equated to either mv square over r, or it is expressed as mr omega square. This is the basic thing that we have discussed many times over. But I would like to relate this to those situations where force, centripetal force need to be worked out, need to be identified with some resolution of forces into 2 components. For example, a bob moving in horizontal circle. A pendulum bob. For example, if initially it is here, if I move it to this position and then I push it away from me, it starts moving in this manner with a certain speed v. If m is the mass, naturally mg will be the weight acting vertically downwards, and tension T is acting in this direction along the string while it is making an angle theta with the vertical. So we need to understand the geometry of this figure. This tension in the string must be having 2 components. One component is along the vertical, which we can show here, and the other is along the horizontal that we can show along this line. Since this is the angle theta, we expect the same angle theta here. So a careful analysis reveals that this must be T cos theta and this must be T sin theta. Clearly, T sin theta is playing the role of centripetal force because T sin theta is that component which is directed towards the center, whereas T cos theta is exactly balancing the weight. So we have 2 equations coming up. T sin theta must be written as mv square over r, being the centripetal force, whereas T cos theta may be written as equal to the weight, because the two forces are clearly balancing each other along the vertical direction. From these two, it can be found that theta has a relationship with the speed. If I divide this equation, equation number 1, by equation 2, I get tan theta equal to V square over RG. So this is the equation which relates the angle theta to the speed of this mass m. Clearly this theta and the speed, it is independent of the mass involved. Even if we have a small mass or a large mass of this bulb, this theta will exactly ensure that the object will be moving with this speed if the radius of this circle is given. So there is a relationship between the angle theta, the speed, and the radius of this circle. We have similar relationships in many other situations, and I will discuss those situations as well one by one. Another situation is a car moving on a banked road. A car, like any racing car, usually racing cars are moving on banked roads. For example, this is the angle that the road is making with the horizontal, and the car is going away from us. As we look at the car from behind, this is the car, and it is moving away from us, moving at a certain speed v in a large circle, because it's a racing track. So usually the radius in which the cars move are something like 2 kilometers. The road is at a certain angle theta. Let's say, as an engineer, you are asked to design all this so that the car at least able to move at the speed of 200 kilometers per hour. Which is approximately 50 meters per second. So if this is the minimum speed with which a car is to take the turn along a banked road, as is often required on racing tracks, large radius is involved because it's a huge track, roughly 2 kilometers or even more than that. Speeds are in this range, 50 or even 60 or 70 meters per second. That means it approaches 250 kilometers per hour in some cases. What should be the inclination involved? Let's say this is the question we need to address. What should be the inclination of the angle so that the car comfortably moves without skidding off the road? Before you solve this problem, you need to understand what is the force which is responsible for the circular motion, that means the force which we can label as centripetal force for this particular situation. In this case, the force that acts on the car normal to the surface is labeled as R. Like most forces which act normal to the surface are reaction forces and labeled as capital R or capital N. This force has two components if I assume that it is making an angle theta with the vertical. If I label this force as R and theta is the angle that this force makes with the vertical, it has two components clearly. One component is along the horizontal and one along the vertical. Again, this component is R cos theta and this component is R sin theta. If M is the mass of this car, the weight is vertically downward, and again this is mg. Again, there are two equations we can write for this situation, like the example we have discussed before. One is R sin theta equal to mv square over R, because R sin theta is the force directed towards the center. Therefore, this force is acting as the centripetal force, and that is why I can write this force equal to mv square over R. The other force, which is along the vertical in the upward direction, and that is R cos theta, that we can write equal to mg, because these two forces are equal and opposite, and that is why the force is not, the object is not moving up or down. So R cos theta must be equated to the weight. If I label this equation as 1 and this as 2, I can dividing equation 1 by 2 gives us tan theta, because sin theta over cos theta equals to tan theta, and R will get cancelled. On the right hand side, mv square over R divided by mg means m will get cancelled, v square over rg, v square over rg. This is the same equation I have derived in the last example. Again, theta, which is this angle, is related to the speed of the car and the radius of the circle in which that car is moving. Now you should be in a position to solve this problem. If you know the radius is 2 kilometers and you know g is 9.81 and you know the speed required is 50 meters per second, then what should be the angle equal to so the car moves comfortably without skidding off the road? So this is yet another example where centripetal force involved is to be worked out first, and then you relate the angle to the speed involved and the radius involved. Another example of this nature is coming next. This example there is a question in the exam related to this example. That is why we are also discussing this. It's important. This is about a marble moving in a large bowl. And the situation is this. Look at this. This is a large bowl in which a marble is placed here initially, and then you push it away from you so that it moves, it remains in contact with the surface of the bowl, but it moves in a circle of certain radius. Let's say this radius is r. In this case, the force which is keeping it here is the normal force which is acting in this direction naturally, and this is labeled as, let's say, force F. This force is the force normal to the surface, so this is the surface reaction force again, and this force, if I again assume that this force is making an angle theta to the normal, because normally the forces are defined with the help of angle to the normal, most cases, but it may be the other way. Maybe they define an angle here, then the situation will be slightly different. Instead of sine theta, the component becomes cos theta. The rest of the maths remains the same. This F clearly has two components again. One component is along this, which is F cos theta, and one component is along the center, and that is F sine theta. Once again, F sine theta is the force which is directed to the center of this circle, and therefore F sine theta must be equated to mv square over r, where m is the mass of this object and v is the speed with which it is moving in this circle, whereas r is the radius of this circle. The second equation, like in the previous two examples, the weight mg must be equated to the other component which is along the vertical in the upward direction. So again, F cos theta is mg. Once again, you have to divide this equation by this, and a familiar relationship, tan theta is equal to this divided by this, in which mass gets cancelled, v square over rg, and this is the same equation that we have derived in the previous two examples. So after discussing these three examples in detail, I expect that you should be in a position to understand the relationship between any angle that is involved. If the centripetal force is initially at a certain angle to the vertical or to the horizontal, you must understand what is the relationship with this angle to the other variables involved. Speed and radius are usually the other two variables involved, where g is the constant here. So you may be required to derive this relationship in some questions, or solve a question simply by giving you a relation like this and giving you a few values. With this discussion, we are in a position to move on to the discussion on the vertical circle. We have discussed motion in the horizontal circle so far. In all the examples we have discussed so far, in all the mathematics that we have derived so far, it was all related to the horizontal circles. But now we are moving on to those situations in which objects are moving in vertical circles. They are Let me, many of you might have this in your mind, but if I take the angle, instead of with the vertical, I have this angle here, then naturally there will be a slight change in the relationship. And let me address that as well. I erase this. Let me quickly describe that situation in which angle is defined with the vertical. Let's say the force is initially is defined like this. It is theta here. The object is moving in this circle. Now this component is clearly f cos theta and this component is f sin theta. So f sin theta here and f cos theta here make the situation slightly different now. But the mathematical steps will be similar. I have two equations again. Number one, f sin theta, I mean this equation now will be equated to mg. So my first equation will become this. And the other equation, f cos theta, that will be mv square over r. Now I am labeling this as equation 1 and this as equation 2 for the sake of convenience, because when I divide this by this, I will get tan theta. So again, dividing 1 by 2, I get, dividing equation 1 by equation 2, I get tan theta equal to g r over v square, because I'm dividing this by this. So this is the new relationship, but this theta is defined with the horizontal instead of with the vertical. So mathematically, things become slightly different naturally because theta is defined somewhere else. But mathematical steps are same, the process is same, the method is same, the method of deriving the relationship, I mean. I hope this makes the point clear. Now we arrive at vertical circle. Vertical circle. A vertical circle simply means the object is going up like this to the top somewhere, and then it falls and moves to the bottom, and then it rises and continues its motion in this manner. It may be a string, it may be a string to which a stone is tied, it may be a stiff rod at the end of which some mass is attached, or there may be a variety of situations there, but your syllabus keeps it simpler. There are not many complicated situations that usually discussed in mechanics. So in physics, most of the time you are asked to focus on two things. Either it's a string to which a mass, a stone is attached, or a stiff rod. How is the situations different? I'll discuss later, but there are many similarities. Number one similarity is that when an object moves in this vertical circle, it is not moving at a constant speed. Its speed is now a variable. When it moves in the upward direction to the top, naturally it will slow down. So if I have a speed here, let's say this is point B and this is point A. If at point B the speed is VB, the object is moving in this manner, the tension in this string will be always directed towards the center. Whether it is a string to which a stone is attached, which has a mass m, or it is a stiff rod to which some mass m is attached, there will be some force or tension that connects the mass to the end of the rod. So this tension is directed towards the center of the rod. Another force which comes in, which was not previously discussed, that is the force mg, the weight. Previously, weight was not the part of our discussion, especially when we talked about the centripetal force. Whenever I mentioned centripetal force, I kept weight out of the picture. But now the centripetal force and weight, they are in the same direction, going side by side. That means my centripetal force now, centripetal force at B, centripetal force at B must be equal to tension plus weight. This simply means if I know the object is moving at a speed VB here and it has mass m and the radius is r, I can write m v square over r equal to t plus mg. This is the situation when the object is at the top of the vertical circle. This is important to understand for another reason. If I want to know what is the minimum speed required by this object so it moves over without falling vertically, I can take this tension equal to 0. For minimum force, for minimum VB, for minimum VB, that means an object should be in a position to move over without falling vertically, so it completes the circle. The tension will be very small, therefore T can be taken equal to 0, nearly equal to 0. In this case, your mv square over r, which is mvb here, this is equal to mg. Therefore, this gets cancelled. So VB square is equal to GR. This is the minimum speed at the top of the circle. So it completes the this completes our discussion for today. Most of the today's lecture was about the previous examples that I have already discussed, but I have added some detail to them. And I have added one more case of vertical circle to it, more of it in the next lecture tomorrow.